Okay, once again, hello everyone. This is our first lecture. I'll try to make it less scary for most of you. The majority of people here are one way or another the computer scientists or data scientists, but then we have quite a few mathematicians and physicists as well, and biologists, of course. How I cannot remember that. Okay, so now if you have questions, the strategy should be you should interrupt me at any point. Just speak up. You don't have to raise your hand, and I'll try to answer it. The more questions I get, the easier for me to understand where the confusions are. And also by asking questions, I may learn something myself. So do not hesitate. Feel free to ask questions. All right, so let's start. I don't know for how long the lecture will go. It again depends on your questions. At least 1 hour, maybe more. We'll see. Okay, so let's. The first topic of the lecture will be on the general framework that we can use to describe all kinds of neural networks. Now, the claim is that you will be able to describe any learning task or any kind of deep learning model, any kind of neural network model. But to understand that anything can be connected to this framework, sometimes work needs to be done. So if you go to the journal club, for example, discussions, there was one very interesting paper that was posted, and I had to go through it and carefully analyze before I understood how it falls within this framework. Generalizing the framework is also possible, although we may not be doing it right away, but eventually we'll see how it can be generalized. Now, the mathematics of it is something you already learned and seen. It's based on the mathematics of artificial neural networks, but the statement of the problem may look a little bit different. The reason I want to carefully go through this is that this is an establishment for us, a language with which we can communicate ideas. And then when you say, okay, I have an idea about boundary dynamics, I think this will be useful, I know exactly what you mean. Or if you say, have an idea about how to change activation function and how it would be useful for such and such learning task, I know exactly what you mean. Because we would all speak basically same language. Although some of us will speak this language with a Russian accent, but that's okay. Okay, so let's go on. So the idea is to define this neural septuple. In the paper, I define it a little bit differently. Here, it will. I think this is a better way of doing this. In this septuple, there are 4 variables and 4 functions. The variables that you will see, the 4 type of variables that you will see, will be related to boundary to the state of neurons X. This projection operator will define the subset of those variables, which we'll call boundary neurons. There will be a W hat, which is a weight matrix, again, a variable, something that can change, and a bias vector, something that can change. I'll go slowly through all of them. And then there'll be 3 functions. The probability distribution at the boundary, the activation dynamics function, and the loss functions. Now, although they're just functions, really there is a lot more underneath behind those 3 functions. And really, it is not correct to say it is just a function. It comes with some dressing that we'll have to discuss. We'll discuss next time. So let's start with the first one, state vector of neurons, and I will state what it is usually, but then I'll ask questions about things that we may do to generalize. So here, the individual components of neurons X are usually represented by either discrete or continuous values. So discrete like integers, continuous like real numbers. Now, integers are something that not often used, and so here I really would like you to think about it. Why or when would you use them, and what would be the problem with using them? And the same for complex number. Now, I can go on here. I can introduce quaternions. We can introduce different fields, and all that interesting. But we'll first concentrate only on these 2 aspects, integers and complex numbers, and see the challenges that come with it. because it's a straightforward definition. You have a state vector. Why not make it not real or something else? And so we'll think about challenges that come with it and the way we can overcome those challenges. Okay, so the integers part. In data science, it's usually called quantization. It's a pity that this term was used, because in quantization in physics means something completely different. We'll get to that at later lectures. But what it means in the data science would be that instead of using real numbers, you average them. You not average, you round them. You use some discretized version of them. Now, in a way, it's cheating, because in computer science, we always use discrete values, right? But here we do a much more dramatic rounding, either up or down. And so those are the notation they use. In fact, pi, if you round it down, you get 3. E, if you round it up, you also get 3. So this is the thing that you can do. Now, it will help you a lot because it will reduce computational complexity. You will be able to do activation faster. You don't need to keep track of all of the decimal points. But there is a problem. There's a problem with finding gradients, with differentiating. For example, the gradient descent method will not work as good. There'll be problems with that, because it relies on being able to differentiate. It relies on the concept that variables are continuous. We'll, of course, get to that method later and see why that is better than others. But at this point, this is just an illustration of the type of generalization that you may do may come with problems. It doesn't mean that you shouldn't do that, but if you do that, you have to evaluate whether your advantages of using it overcome the disadvantages of using it. So now this is somewhat trivial. Again, usually that's how lectures proceed. To start with something that everybody knows, and then gradually start introducing things to make things more complex. Here's another one, complexification. A little more challenging. Not, again, mathematicians, physicists, we use complex numbers all the time. In data science, people heard about them. They've used them maybe in high school or in some math courses, but never actually used it. So what's the problem? What's the problem of actually making the state of neurons being complex? We can easily do that. So one of the advantages, and again, I will say the word that some of you might know, analytic continuation is good. It basically makes things less constrained. So and it is always good. And we'll come back to that jargon of constrained versus unconstrained very often. The many problems of machine learning when some things don't work come from actual constraints that you put on the learning system without even realizing it. And one of those will be constrained on the weight matrix. You develop certain architecture, write down certain neural network, and if you do it in a constrained way, they may be harmful for their learning evolution. Okay, but there is also cons, and that comes with the fact that once you evaluate a function of a complex number, it has many branches. I'll explain what it is shortly. And that's a problem, because when you go through the activation dynamics, basically neuron collects all of the inputs, sums them up with some weights, adds a bias, and then here is time to take all this expression, this number, and put in an activation function. And if this number is complex number, then you may have multiple answers to what the output should be. And here's an example. So let's take a simple function, exponential. Exponential some input, x plus iy. You may think that whatever I say put into x and y, I can always get a z. There will be some complex number. And that's true. But now let's look at the other function, log z, which is basically can be obtained by taking logs of both sides. You have a log z, then equals to this expression, x plus iy And here what you see that there is something else that I can add, and the expression would still be correct. And that something else is 2 pi n. So you can add here and replace question marks with 2 pi n for arbitrary n, and that would still be a correct expression. That means that the log of z is not uniquely defined. And if for some reason log was your activation function, which isn't usually used as activation function, that would create a problem. And that is a problem is not unique for log. It appears everywhere in the evaluating complex numbers. And here how it looks if we are to produce a graph of that function, right? So it has to be a three-dimensional graph because input is a complex number, so it has a real and imaginary parts. And then output, you're trying to, it's also going to be a complex number, but what's the point here is that the imaginary part of that complex number will be multivalued. So you can define this function by doing what's called analytic continuation. And so you, by making small steps from here to here and doing your Taylor series expansion, you can understand what it is. But once you go around the zero and come back, you would want to come back to where you started, but you don't. And this picture, the spiral picture goes on. And so basically, if you are trying to calculate a log of any complex number, there is a sequence of numbers that the tower of numbers that can be used as an output. And then the question, what we use as an output? Not clear. Sticking with one branch will only work if you think about this function locally, but that's not how activation function work. And so with a global picture, this will not work. However, there are other functions that don't have this branching problem. And then they may be usually reducible to just having two real numbers, like two neurons, which are real. And then we're not gaining much by doing this generalization. So I call this as a trivial generalization of the neural septuple. And one of the, somebody posted again another paper about generalizing the field of states of neurons. And then this is again something we can discuss when it will or will not be useful. So this is just a statement that there are problems that may come with it. Okay, questions about that?
Yes, I have several questions, Vitaly. First question, actually, it was you who asked when can we use integers as a state vector? In state vector of neurons, maybe we can use integers when input data is not continuous, output data is not continuous, so we're trying to build a map between integer
absolutely.
Integers.
So sorry. So for example, it's always the case, usually the case, like with images, you have pixels, right? So it's actually discretized. And now the statement here is that within the bulk, within the sexual neurons, how do you propagate those data? Do you want them to be continuous or discrete?
And another question. Well, if we use complex numbers, there is a problem with many branches. Did somebody try to use some rule to choose a branch?
Yeah.
For example.
I understand. So I've said it in passing. If you only work with one branch, it will only work if your state changes locally. So as long as if your state start changing globally, so for some training data, it is here, others it's here, others it's here, and then here, then you're stuck with a multi-branching problem. Now, if all of the data of the entire data set just make your state take values locally, then you don't have a problem multi branches, but you also don't have a benefit of complex numbers. You can actually replace it with just a couple of functions, and not clear what this would be useful. But I'm sure people tried everything. So
did people try to use to choose a branch according to some probability distribution, like something like normal distribution? When the most probable branch is 0, the next less probable branch is 1, less probable second, less probable third.
Yeah, that's actually a good question, and I will leave it until later. Next time we'll probably discuss it. It has to do with the fact each one of those boundary distribution of training data, activation dynamic of A or loss function may have randomness in it. Not usually taken. So activation dynamics is always usually deterministic. But adding some kind of randomness to this, as you said, choosing a branch, for example, may produce interesting results. And that has to do with the discussion that we'll have last time. All right, so now we know what this neural septuple is. Let's see how much freedom we have into generalizing dynamics. And we'll discuss all three. So I'll leave that question until last time.
Thanks. And what about other types of numbers, like p-adic numbers, z-adic numbers?
As I said, all this is the game that people can try to play, right? Now, if you choose to play this game, it's a fun game, but at the end of the day, you have to prove either advantage or disadvantage of using them. Okay, Artem, you ran out of your questions for today. Any other questions?
Hi, Doctor. Can you hear me?
Yes, I can.
Yeah. So I have a similar question to Artem. So, like, by mentioning multiple branches, we can have with the complex number activation. In my understanding, it's like similar to setting this y plus question mark, setting it to like a single phase, right? Set it to one. Yeah. So, like, let's say 0 to 2 pi, we sort of quantize that imaginary part. So, like, is it equivalent that we quantize this part and we like restrain the network to only one cycle, to only one branch, right? So
that's right. So it's all good, but then you have to tell the network what to do at the boundary, right? So so let's say you only go from 0 to 2 pi, and let's say your state is right here. Do you really want, if you change your training data by a tiny bit, the state of the neuron jump dramatically? And if you do allow that, the system will become unstable.
I see. So
like
that the limits.
You slightly perturb the image of the cat, and all of a sudden it becomes a dog, just because your system,
I see.
Chose the wrong branch. Yeah, but good question. Yes. Other questions?
Thank you.
Sure. All right, so let's go on. Let's go to the next one, boundary projection operator. Now you can either do that, or you can, for the first two places in this neural septuple, you could just say, let's define the bulk and boundary neurons. This would be equivalent to defining all neurons and then a projection. Projection operator here can be thought of as a matrix with all the diagonals are 0, and the diagonals are either 1 or 0. 1 if the corresponding neuron is the boundary, and 0 if it's in the bulk, meaning a hidden neuron. Okay, so it's important, right? Because we are going to be treating the bulk and boundary neurons differently. Again, using the standard terminology in machine learning, we are going to be treating input, output, and hidden neurons differently. We will do that when you define a loss function. We'll do it when we define a boundary dynamic function. And so that's important to have that distinction between what degrees of freedom are for the boundary and what for the bulk. But this is a new terminology that we enforce. It's very useful when you're trying to apply physics theories. And so from now on, we will be calling the input or output neurons as a boundary neurons, and the hidden neurons as a bulk neurons. Okay, so now, but the question arises, do we have to subdivide it further? Do we really need to define input and output projections? Now, for some learning tasks, there is no distinction between input and output. Again, in the journal club group discussion, I've written a paragraph or so about the paper where the whole idea of the author was to move output neurons to the input and then do something interesting there. So it's a good question. So whether do we need to really do it all the time? Do we need to have a separate definition for input and output neurons? Now, the statement that I'm trying to make here that you don't, and because this information is redundant, really by looking at the weight matrix, and we'll get to the weight matrix soon, this will not be the weight matrix that you see often between the layers. This will be just one matrix for the entire neural network. Okay, and from that network, from that weight matrix, you can always see which neurons are input, which ones are output. So this information is redundant. Now, moreover, when you define a loss function, and if your loss function is the boundary loss, then it is usually defined on the output neurons. Now, again, this is not such a strong statement as the previous one, because after all, you don't need to define your loss function for the boundary neurons, and so for the output neurons only. And so the second part may or may not be the feature that would distinguish and tell you which ones are input and output. By the way, those slides I will be posting to the Telegram chat, so you don't have to write anything down if you don't have to, and also the recording of this meeting will be posted to the Telegram chat. Okay, so basically the bottom line that the splitting of the boundary neurons into input output doesn't generalize the framework. We're not going to gain anything new. There are generalizations that I'll either discuss or we can talk about later, either I discuss like next time or some other time. But it seems that most of the learning tasks are conveniently described in this framework, and that makes it good. So then we can really, when somebody has an idea in machine learning, the person can just come and say, okay, look, this is what I want to change. I want to change the activation dynamics or the weight matrix or whatever. And then we know exactly what the person means. Questions on the boundary projection operator? Okay, now the other thing I want to note that this X state of neurons should be thought as a column vector. I didn't say that. So it's like column of numbers. And so this boundary projected vector is also column numbers. The only difference is that this boundary one will have a bunch of zeros corresponding to all of the bulk neurons, all of the hidden neurons. Okay, let's move to the third one. This one is really very non-trivial. And there is so much research that can be done on that thing alone, trying to understand what is the training data set, how it should be streamed to the network, and there is it's just how to do that, like to reduce overfitting. I'm just like throwing random ideas, how to change it such that the neural network learns faster, becomes more stable, learns better. It's all those questions you can ask, and the theory of this boundary data for now poorly developed. Let me just put it that way. Okay, so but what is it? It's just a distribution. It's a distribution of the boundary neurons. Now, typically it's given as a sum of delta functions for each data point in your training data set. And if that's the case, there is no ordering. It doesn't matter in which do I, like, let's say again, go dogs and cats. One question, does it matter whether I first stream and show all the dogs and then all the cats? Should I randomly choose from this data set of cats and dogs? Should I alternate? First I show to the neural network dog, then cat, dog, cat. What's the most optimal, right? So there is, or maybe some other variations of statistical versus deterministic way of streaming data. All this is poorly known, and so that has, the question. Sometimes, even if your data set doesn't have ordering, you want to give it ordering. You want to first maybe stream all cats and then all dogs, or maybe your data set already comes with ordering, right? So maybe you are trying to look at the video some movie. So there is order, there are frames, and the frames come in order. Maybe you want to disturb this ordering, and this will help learning of the neural network, or make the learning more efficient. All those questions are mathematical, they're well defined, fully investigated. So let's go on. So now here I just summarize pretty much what I said. Usually this is what it is. The probability distribution is just sum of delta functions, and they may have ordering, right? So here I assume that x1 to xm has no ordering. This is just integers. But what if there is? What there is, x1 has to go before x2, etc. So in physics, we call ergodicity when the system, when it doesn't matter for the system where things are ordered or not ordered. Now, and in this case, when the ergodicity, we say, is not broken, then the ordering average equals to a sample average. So whether you, by ordering average, think about like time average. So think about the samples that are shown one after another within some time interval difference. Now, sometimes it's broken, and most interesting things, the ergodicity is broken. In physics, we call those systems a glossy system. There are evidence suggesting that this is what can be beneficial for the machine learning systems. For very simple, like few neurons, very simple machine learning tasks, you can actually look and say, all right, let me introduce ordering. Will that make things better? How will this affect things better? And then you can show analytically and also numerically that for certain tasks, it will be beneficial to introduce, even if you didn't have ordering before. Another way around, if you did have ordering before, maybe you should break it. Not completely, not like make it completely smooth, but minimal. Okay, and then coming back to physics and biology, the broken ergodicity is everywhere. This is where interest in physics and biology is, and so is it's expected. So we're now developing a neural processor for a computer that would do learning at the level of hardware, and there are evidences suggesting that the best learner, physical learner, we'll touch on those topics later, should also have a broken ergodicity, and so the ordering does matter. Now, how to define this thing with ordering? So here I wrote only one formula, right? That has no ordering in it. How to define it? And that takes us to the realm of stochastic processes, right? We want to have both. We want to have some deterministic part and also some stochastic process. What kind of stochastic process would be needed to have most efficient way of streaming data to the network? Lots of interesting mathematics there, lots of unanswered questions. We'll talk about this more next time. Questions about training data set, if there are. I'm sure there'll be more, but this is very important. How do you show the data? You have a training data set, how do you show it to the network? Okay, so let's move on. Weight matrix. Again, I'm going to throw in some mathematical jargon that is not used by data scientists. And the reason for that is because it's useful. And secondly, because it actually shows the main point I made before, is that if you introduce constraints on your systems, you better know what they are, and you want to pay attention whether those constraints are prohibiting the network to perform well. So one usual constraint people put on the system without even thinking whether this is a constraint at all is by making your architecture of the neural network being feed forward. Meaning there is a layered structure, you have input layer, from input layer you pass it to the second layer, to the third layer, and so forth. There's all the connections go one way. Now imagine all these connections representing an adjacency, representing a graph. And then now let's go a little bit dive into the graph theory and say in the graph theory, the graph would be represented by something that's called an adjacency matrix that shows which neurons, which nodes are connected to which node. In our case, nodes are neurons. Okay, so you have that graph, you have that adjacency matrix, and it's a feed forward. So all connections go in one direction. And now you say, all right, let me take this matrix and let's keep raising it to some power. 1, 2, 3, 4, 5, etc. At some point, after a few raising to the power, you'll get zero matrix. And the reason for that is because matrix kind of counts loops in your graph. And in the feed-forward architecture, there are no loops. They're all one directional. Everything flows in one direction. And so after a certain number of time, you raise it to the power, and specifically when n is equal to the number of layers, after that, your weight matrix becomes zero matrix. In mathematics, those matrices are called nilpotent matrix. One property of those matrices that all of the eigenvalues are zero. Okay, that could have been expected because basically when you raise, the only way for you to get a zero matrix after raising is to make sure that all eigenvalues is zero, because if there was one which is non-zero, that would be effectively just be raised in the diagonal form. It would be just raising this non-zero eigenvalue to higher and higher powers. Okay, but that is a constraint. So if you say, I'm only interested in the weight matrices that have this particular form, that you are not allowing your learning system to explore anything else. You've put that wall and said, okay, even if you wanted to make this network unconstrained, even if you think it would be beneficial for learning, there is no go. You introduce this constraint. So libraries like TensorFlow or Keras would just say, there's no go. You cannot do that. And so then you cannot explore actually the richness of the weight matrices that you may have. Okay, so this is again pretty much summarizing what I just said. When you raise to the power, you basically, each element of w to the nth power of ij is a sum of all possible paths between j and I. And if there are no paths which are greater than some number n, then this sum has to be zero. And this is what you will get in the feed-forward structure where all of the directions point in one way. Okay, so this is again the statement. Now it also holds for the transpose matrix. So think about transpose matrix is again a graph. It's a directed graph with now directions pointing backwards. So from output layer to the input layer. So the same thing will hold. This is very important because very often when people think about weight matrix in machine learning, they think about, okay, there's one weight matrix between layer 0 and 1 and 2. There is another weight matrix between 2 and 3. There is a third between 3 and 4. Okay? And this is the wrong way of thinking about this. More generally, there is just one weight matrix that just describes all connections. And all this layerness are just encoded in this property of the matrix. And this kind of the approach we're going to be taking, right? So every single architecture, every single neural network just has a property of the weight matrix that you assign to it. Now, when does it make sense to introduce constraints? Why would it make sense to introduce constraints? By introducing constraints, you reduce the number of trainable parameters. So you make things learn faster. But at the same time, you constrain the system so it doesn't train the other elements of the weight matrix which you set to 0. So there is a balance. You should only set a constraint in the weight matrix where we're absolutely confident that those 0 components of the weight matrix are useless. So for example, the weight matrix which connects this red circle node to here, which skips a level, this respective element of the weight matrix would be 0. But what if you need to skip layers? You would never know because you put such a constraint. Sometimes you may want connections to go back in between, or maybe you can want to have connections between neurons on the same layer. You would never know because you've put that constraint. Now, when I said that TensorFlow and Keras, they don't allow that, of course, I wasn't completely honest. There are ways for you to do that, but they're hidden ways. They are not straightforward ways of how to remove the constraints. Okay, questions about that?
Oh, yes. So my question is, how often do neural networks have nilpotent weight matrices? Like, is this a very prevalent case for neural networks, or?
Right, so whenever you hear feed forward, that's
okay.
no. So that's kind of synonym word for the nilpotent. And again, there are many other matrices which have many other properties, but they're not usually looked at through the properties of the matrix. Like one analysis of any matrix you can do is eigenvalue decomposition, right? Finding a spectrum of the matrix. And you may say, all right, so I have a particular learning task. What is a preferred spectrum for the weight matrix? Well, you can try to drive it analytically, study, what things, or numerically, brute force. Just start with the unconstrained and see where the matrix would evolve. So there are many things that you can do by actually going from just drawing graphs and into studying spectral properties of weight matrices. There is another important matrix that I'll introduce maybe next time. I call it the G matrix. So it is similar, analogous to what's called as the Laplacian matrix or Laplacian operator on a graph. And it's very close to the Laplacian that we study in physics or mathematics, basically the matrix of second derivatives, right? D squared dx squared plus d squared dy squared plus d squared dz squared. So this is an operator that's called Laplacian. Now, if you assume that your space is a lattice points, and then you connect them with the nearby lattice points with edges, then for that graph, Laplacian operator of the graph would be equivalent to Laplacian that we study in continuous spaces. But the idea that in graph theory you can generalize it further, and that operator plays an essential role in the statistical analysis, perturbative statistical analysis of the machine neural networks, artificial neural networks. Anyways, this is very important point. So if you are surprised by the fact that there's only one weight matrix, and you want to say then you're missing something. So it's usually the way people think about weight matrices. There are many of them. No, there is just one that has properties, as opposed to many that not square. And this is a square matrix too, right? So it's okay. So let me. Artyom is allowed to raise a hand because he was banned from asking more questions. Okay, Artyom, I'll give you a chance to rehabilitate yourself.
Thank you. So if we are talking about feed-forward neural networks, the information kind of flows only in one direction, right? For
the feed-forward, that's right. Yes.
But for example,
activation information flies in the one direction. But there is a learning information that goes in there.
Can we use the same neural network to launch information in other direction?
Oh, but that's the idea, right? So basically, you're saying that you've constrained your weight matrix to only allow information to flow one direction. Why? Well, because you had the idea of this backpropagation. You had an idea that output neurons should only be used for defining the loss function and nothing else. But there is more to this. There might be, it's essential to connect your output neurons and have them. And in fact, again, I'm referring to that paper that was posted. Somebody posted, Peter posted in the Journal Club, where that's exactly what happened. So the guy said, all right, why don't we just take all output neurons and make them think about them as input neurons, allowing information to flow from them? What will happen? And so he studies that. So yeah, so here we have all those abilities. Okay, other questions? All right, let's move on. We are 4 7th way through, bias will bias is often thought of as a simple generalization and may not be essential to be here. Why? Well, because I can always think about one neuron that has always state 1, it's always state 1, and then this neuron is connected to all other neurons by edges. And then bias is nothing but the value of the weights on those edges. So really, then you look at it and say, well, then really putting it here is not going to generalize the septuple, yet I still put it here for other reasons. And the reason is symmetries. There is one aspect that will be appearing and reappearing over and over, symmetries. And here is a good way for me to illustrate what I mean by symmetry in a neural network, and also keep in mind that symmetries play a completely essential role in all of the 20th century physics, right? So if you say there is one result in physics that was discovered in the 20th century, that was it. They said, all right, let's identify symmetries, and given that, let's write down theories. Okay, and that's what this question is about. So you have some neural network, maybe septuple, and can you define an equivalent network with vanishing biases, right? No biases. And that was it. This is what I said. Yes, you can just set one neuron to be equal to 1, okay? And then change all of the previous biases to 0, B prime, and adjust all of the weights that were before to be the same as they were before for all j's not equal to this n+1 neuron, and to equal to bi for all the neurons, for all j's that are equal to n+1. It's a transformation. It's a transformation from one set of biases and weights to other set of biases and weights. This doesn't change anything for the neural network. It will still be learning exactly the same way. Nothing will change, yet there is this transformation, and we call this symmetry. There are other symmetries that I didn't write here, a more trivial one. They can be a permutation symmetry. Really, what you call, very often you can have permutation symmetry. What you call neuron 1 and you call neuron 2 is irrelevant. You can really permute all of the neurons, and then there will be a different order of those neurons, and yet they will still be representing the same system. I'm not discussing here permutation invariance. It's trivial. We can talk about that later. It may actually be important for other things. But let's talk about this. This is exact symmetry and boring, just like permutation symmetry. This is approximately symmetry. Approximately symmetry that you will not have for starters in your neural network, but it may develop. It often develops. You can look at the papers that will show you. So one of them is this, the emergent invariance. Well, there are other papers, yes. So there are many papers that emerges. But let me tell you about this particular symmetry, what this is. Let's say you have a state neuron that is approximately given by some value. So yeah, you change data set, you change images or whatever your training data is. All states of all neurons keep changing, but let's assume that there is one neuron where all those different boundary conditions, boundary neurons, they always lead to the same state of the neuron. Then we call it a dead neuron that actually stays at a constant value and it's not needed. You can eliminate this neuron. Or you can leave it and then adjust the biases and weights that go to or from that neuron. And here's the transformation. And in fact, if you do this training, you can look at individual neurons, plot a distribution of states that they take through one epoch. And for that dead neuron, you'll see it sharply peak about one state. So for example, for sigmoid activation function, the state of the neuron would be at 0 or 1, or close to 0 and 1. Okay, so here is the transformation. We had some bias and weights, then we transform it now, not by discrete, by a continuous parameter alpha. Alpha is some number, any real number. And I change bias to 1 minus alpha bi, where bi is this bias that the neuron had before. Okay, so now what about the weight? So the weight now adjusted this way. So it will be the same weights for all the other, for all the J's that are not equal to this K neuron. And it will be different for all the J's which are equal to the K neuron. So for now, just look at this as some formula, right? So some linear transformation. You transform W to some other new W. You transform B to some other new B. Okay, but now let's plug in into this expression. This is what we had before as input to arbitrary neuron I. And this is what we're going to have after. Okay, so now here is what we're going to have the state for this neuron. So this is the state. So it will go right here. Okay, so this is like weight matrix. This is the weight matrix multiplying the xk. Okay, and then here we have the for the jth neuron we have this new modified for this new modified bias. This is the new modified bias. Okay, so what happens now? In comparison to what we had before, we had this modification minus alpha bi, right? However, this minus alpha bi will be canceled by this second term when x is close to x hat. And so then you will end up, this expression will end up being the same. Meaning that every input to the any ith neuron will be the same. So this signal that goes from the kth neuron to the ith neuron will still be the same. Nothing will change. And that's a symmetry. That's a symmetry that allows us to actually remove this neuron at all. You can actually eliminate it. Okay, or make this small continuous transformation. And there are, this is one example of a symmetry, of emergent symmetry, of not exact symmetry, but there may be others. This transformation actually is similar to the first one, right? The only difference now, we have this nth neuron, which is not equal to 1, but it has some value. Of course, 1 here was not needed here. It could have been any constant. But the other point here that this is not a sharp transformation, just making bi going to 0, which would be the case if alpha was equal to 1, but making bi go to anything we want. Okay, now those are the symmetries that often called flat directions. They're the directions along which there is no benefit to learning. So if you think about the space of trainable variables, there is this one direction. You can keep changing your b's and w's in that direction, but they are not changing anything. So this is like a dumb direction. In physics, we can call it a gauge symmetry. And we use them because in physics, we identify them and they tell us about what kind of theories to write. Here, our job also is to identify those flat directions, because if we know them, we can just say to machine, don't train there. There is nothing there. It's a symmetry of the system. Okay. Moreover, you can take out the dead neurons. You can use this symmetry to eliminate this trainable variables, which is just essentially the same of saying there is a direction, don't train in that direction. It's useless. Okay, this is a simple example of the symmetry. There are more complex symmetries, but it is essential for machine learning system to be able to identify those symmetries and then eliminate. And if you do that, then you're in business. Then you're then you can reduce the number of trainable parameters. Then you can make your neural network perform better. So the one paper I didn't write here, but there is a paper that is actually more relevant. Those are more general things about emergent symmetries, but there is a paper which really deals with the dead neurons. It's called bio-inspired machine learning. the replication and program death. The idea there is exactly that. Identify the poorly performing neurons which have either this property or a more general property of being useless, and remove them. Okay. It's inspired by biology, but it is just a statement of finding the symmetries and then using that fact. Questions?
Excuse me. So can you remove the neurons before the training, or is it after the training?
Yeah. So in the first case, you can just remove it, whenever you want, because it's exact. In here, it's emergent. So you removed it, and then why? Right. So you had this degree of freedom. So it's usually you have to wait. You have to see the symmetries emerge. You identify the symmetries, and you reduce your system. Now, in this paper, which I noted, the paper on the bio-inspired machine learning, what you can do, you can remove the neurons, okay, because it was useless, it was dead. Then find neuron that actually is struggling, has most sensitive, its changes of its state is most sensitive to the loss function. And then rewire your network such that it uses this freed neuron in the right way. And then what you're doing two things at once. You're eliminating the symmetries that are not needed. And then you're reusing the freed memory and processing power to help those spaces in neural network, those neurons, those connections that need to be helped with. We'll talk about this in more details. This is just telling you probably main message here is symmetries are essential and of essential importance. Now in physics, we already know how to work with them. In physics, we assume the symmetries are exact. We don't know for sure. Here, we know that the symmetries are not exact. Many symmetries are emergent. And then having the ability to identify those symmetries and then improve your algorithms using those symmetries is essential. There are one other place where symmetries will be used, and again, the symmetries are used always either someplace in this neural septuple. So there is one other place the symmetries are useful is in this boundary dynamics. Okay, so certain directions you do want to train, others you don't. And when you do train, there is essential or inessential information that you want to obtain. We'll talk about this later and not now, but symmetries will be everywhere in these lectures. Asifur, go ahead.
Thank you.
So, you were not banned from asking questions, only Artyom who was banned. So yes, you can just speak up. Yeah.
Yes, thank you so much. So my question is, so in neural network, one thing neural network struggles with where it has to represent weak correlation. So can we use this symmetry to so whenever it's optimizing, it actually overfits to the neuron that have better performance or just with respect to the mapping, but it loses the weak correlation between data and outputs. So is there any way this symmetry can be used to
enhance certain, you're talking about weak symmetries, right? Weak correlations, right?
Yeah, exactly.
Yeah, you can enhance. This is the whole point, right? So and now it's more relevant to something other that I've listed in the topics we're going to discuss. It's called the RG idea in physics. Okay. Basically, you want to perform a transformation on your data so that certain features that you do know are important become enhanced and other become suppressed that you think are not important. It has to do with what we call relevant and irrelevant operators. I mean, I completely understand that non-physicists would just be completely lost with what I said, but the idea is that you identify what is relevant, what is irrelevant, you suppress what is irrelevant, you say it's not needed, and then you enhance what is relevant because it is needed for the performance of the neural network. And so that's why I said about the symmetries for this P sub D, I was talking about exactly that. You need to identify what they are, and yeah. So I think I'll just close this slide with one more remark about a convolutional neural network that has to do with a weight matrix. right? So it's a certain structure with a weight matrix that proved to be very well for certain boundary data here, which are kind of images. And the reason for that it works well is because the weight matrix knows about the symmetries of the boundary data of images. And the symmetry there is a shift symmetry. So basically your cat could be here or here. They should not change the loss, or can be rotated. And that is the symmetry that comes from here and then gets into W. Now, yes, you've guessed that symmetry because somebody look at the picture, said, look, there's a shift symmetry, but very often you cannot guess it. And so you have to make sure your network discovers it before you can impose that. And that is why the one other paper that somebody posted, which I thought was very interesting, is to see how the data itself can make the symmetry that is present in convolutional network emerge. Okay, and then once it emerge, you're in business, you can use it. Okay, Asifor, if I answered your question, you should remove the hand.
Yeah, sorry. Thank you.
Sure. All right, so let's, we are past 1 hour and I still have to go over 2 more slides. And I understand the attention span for people is usually less than an hour, so I'll try to, and that was a lot of information, so, but I'll try to go faster now. Activation dynamics. And now we usually think it's as a just function. People try Sigmund, hyperbolic tangent, ReLU, but what is the reason, right? You want to have a theory of understanding which activation function are used and which not to use. Not even, and the other aspect is activation dynamics is completely deterministic, right? It's a fixed function. What about adding a probabilistic part of it? What is it again? What is it what if we want to think about this as some kind of stochastic process, which with some probability distribution? Will it be beneficial or not? So all those things we're not discussed with enough rigor. But here I'll just describe the deterministic Fs when they are fixed functions, and we'll just say how we can think about why one or the other function may be better or worse. So there are 3 things that usually need to be present for the weight for the activation function. One, the activation function has to be easy to compute. So if it's a complex function that evaluate, this will slow down both evaluation and then the backpropagation when you're doing the derivatives, right? When you backpropagate. So it has to be easy to compute. The second one, it has to be a non-constant, because if it's a constant, then we just argued that it would correspond to a dead neuron and nothing interesting would happen. Or neurons become dead, which is what we said. So it has to be easy to compute, non-constant, and the third one, it must be nonlinear, and that's actually essential. Like very often, people would just stick into a layer with a linear activation function. That's useless. You can eliminate this layer, and that's not going to affect your performance. And here is the proof of that. So you have 2 layers, basically, and here I assume that all W, it describes all layers, but basically the entire weight matrix is linear. The activation function is linear. And then if I take 2 steps of the activation dynamics, this, whatever I highlighted, is the first step in the activation. This is the second step in the activation. Of course, it's all equivalent to a single step of the activation with appropriately defined weight matrix and with appropriately defined weight matrix and bias. Okay, so here we go. It's another symmetry, right? So we do not, and that's why there is no reason for actually using linear activation functions, because you can reduce your complex and deep neural network with just a single step. After appropriately redefining the weight matrix, so this would be your W prime, and this would be your B prime, this whole thing. So now you can think about new activation functions that satisfy all three conditions, right? So we wanted, once case, we want it to be easy to compute, but okay, let's forget about that for now. It has to be non-constant and a non-linear. So there's examples. Now linear isn't going to work, so it's go away. ReLU is interesting, right? Because it's non-linear. It's not linear everywhere, and also easy to compute. But it has the problem here that it is constant on that side, and so if the system gets stuck here, then this neuron becomes dead, and so there is this danger. It's also the same true for the hyperbolic tangent or sigmoid. When the system gets stuck here or here, the neuron becomes dead, and so you can eliminate it and not use it at all. So now the one way of thinking about this is maybe, so you don't want to have flat directions and you don't want it to be constant. So therefore, ideally you want it to go, up and down, maybe like sinusoidal. And the people had tried sinusoidal activation function. There are other problems with stability with that, but that's again beyond what we have to discuss now. Questions on the activation functions? Artyom, okay, you're allowed to speak up.
Okay, is there some analytical approach to choose the best activation function for our needs?
Yeah, so that should be done. And people had done that by considering, so what you should do is the following: consider ensemble of functions, have some kind of orthonormal set of functions representing it, and then make it your activation function be learned as well. So you can do that. People had tried that. Now, it is absolutely true that for some learning tasks, one activation function will be better than the other. At this point, this theory of activation function isn't developed to the point where we can, by look at the data, do statistical analysis of the data and say which activation function will be better. So there's a lot of missing steps in analytics there, as well as the other thing that I said. Do not underestimate the fact that activation function may also have a stochastic part of it. So Boltzmann machines have some features of that as well. So having a stochasticity to this activation function is also important. Presumably something we'll discuss in more details next.
Thanks.
Okay, so let's move to the one most important. I would not be giving these lectures if there would not be this loss function. Loss function changes all of the games we're used to playing in physics and mathematics in the way we model dynamical system. It introduces something that is not, so in physics, for example, we have the boundary dynamics, boundary conditions, we have activation dynamics, basically classical laws, how things evolve, but we don't have at the same time this other dynamics. I'll talk about more connections to physics later, but let's talk about this. Now it's a function of everything you can have in all variables. So in biases, weights, boundary neurons, bulk neurons, just write whatever you want and it will be your loss function. Now, it doesn't mean that anything you write will be useful for whatever learning task you have, but it is it. Now, however, there is a difference between the loss functions of supervised and unsupervised learning tasks. And so I'll give some examples right now, and then I'll let you go. And then you can also ask, what about the reinforced learning, and can it be also described using the septuple, and what kind of loss function would be defined for the reinforced learning? So here is the answer to all the three questions. For the boundary loss, it is nothing but the difference between the state of the boundary neuron with the state that would be at the boundary neuron if we have one more step in the activation dynamics. So here we are not activating the last layer in this definition. And so the output neurons are assumed to change only due to the boundary dynamics, only when you update your boundary conditions. It is the matter of how you define it. Of course, you are free to activate it until the very end, and then have two layers in the output, one which belongs to the bulk and the one that belongs to the boundary. It's not necessary. Now, the reason why I only have this one projection operator here, because you would think you want to have a projection operator for those two guys and also a projection operator for these two guys. Now, if you take a transpose projection will jump here, and it will be projection transpose times projection. Transpose of the projection operator is just the projection operator, and square of the projection operator is just the projection operator. Remember that projection operator is nothing but the matrices that have zeros off diagonally and ones and zeros on the diagonal. Now, the boundary loss for supervised learning is usually defined on the output boundary. Nothing stops you from defining it also on the input boundary, but that's kind of example of what the usual supervised learning is. Once you have that, then you in business, you can differentiate it with respect to different variables and see how to deform, and we'll discuss it next time, how to deform your system such that the loss is minimized. Now, those variables are also a function of the variables, a function of the variables, a function of the variables, and that now we are talking about the backpropagation. So it's a function of a function of function, and then to actually differentiate it, you use the backpropagation technique, which is just trivial mathematics of a function of a function, of differentiating function of a function of a function. Okay, now what about unsupervised? For the unsupervised, there is no output neurons, so you cannot do that. However, you can still define a demand of this like kinetic-like term. So again, in physics, we would call this a kinetic-like term. And you can still define this kinetic-like term for the bulk neurons, where your demand is for the state of neurons not to change much. If you want to, just like here, not to change much from one step of the activation dynamics to the other. It's your choice. Now, usually the more interesting one is this, and this is used. You are trying to come up with a function of those variables and say, well, let's minimize it. So here's an example where you can have a local objective. For example, you want your bulk neuron to classify. You want to either be +1 or -1. Then you develop this potential to have two minima at +1 and -1, and then the system will punish anything in between, and will just go to +1 or -1, trying and it will try to classify for whatever use that may be. The other one is called the L2 regularization of weights. You do not want weights to run away, to become very, very large. And if that's your requirement, then it's effectively equivalent to putting this term in the loss function, which is a trace of W transpose W. What this is just sum of the squares of all elements of the weight matrix. This is what it is. Okay, but let's take this reinforced learning example. Here is your neural network. People would call it an agent. It has a reward. So reward is definitely your loss function. But this reward depends on the state of the environment that you get by acting on the environment, right? So what is it happening here? It's happening here that there are some states of neurons that back react on the environment or on the boundary dynamics, right? So you change it, and that back reacts here. So in terms of septuple, this guy is changed by the dynamics of this guy that we'll be discussing next time, is modified by the actions. But the action, you can think about the state of one of the neurons that you get there. Okay, and that's okay. That allows you to come up with a more advanced modeling of what the boundary dynamics is. Remember, today we discussed it can be just a probability distribution. It can have time ordering. Now we have a new feature. It can depend on the state of a given neuron that you generate within your system. Okay, that's one distinction. And that we call action, how we affect it. Now, again, I'm trying to wrap up so that we don't spend more than 1 hour, 15 minutes. For the reason is just the attention span is not that long for most people. So there are different hyperparameters, and one might ask, all right, can you take all those hyperparameters and actually describe them in terms of septuple? Can you? And so let's go over some of them. The question is actually very difficult, and there are some of them you can, others you cannot, but let me go over some of them. So let's take a network topology. That's the thing we spend the most time talking about today, meaning what is the weight matrix should be. Feed-forward topology, meaning that there is a certain graph, certain constraint on the neural network. And so anything that has to do with the topology of neural network is just reformulated in our formulas in terms of the weight matrix. And so that's easily adjusted into the definition, into the neural septuple. So there's nothing new. It's not a hyperparameter, it's a parameter. Okay, it's a learning parameter. You can have a system learn the topology. Okay, what about the learning rate? The learning rate is something that, again, we'll talk more about next time, is a parameter that would go into the multiply gradient of the loss function. Now, by looking at this, you will see that this parameter can also be absorbed into the definition of loss function. So once you have loss function, moving this learning rate in the loss function or outside isn't changing much. Mini batch size is another parameter that is unique to the dynamics of learning, and it appears into how many samples do you go through before you decide to make your gradient descent. And that is again something that is imprinted into the learning dynamics. Okay, and the next time we'll talk about those three things, because they really form the key elements of the machine learning system, the existence of all three, and we'll discuss the ability how we can generalize it. What are the freedom we have there? We'll discuss a little bit about boundary dynamics. We'll dig more into that. We discussed a little bit about activation dynamics. We'll discuss more of that, and learning dynamics is, of course, the king of all three. It's what makes machine learning system a much more difficult system to analyze than anything we had to do with physics, with an exception of gravity. I'll argue why gravity is kind of, without going into details, because I do not expect people to know general relativity or anything like that. But I will describe roughly why the learning dynamics is so unique and interesting. Okay, so we way past our bedtimes, and so are there any questions, comments? You can ask now, you can ask tomorrow, during my office hours. Go ahead.
I have one question. So it's related to the previous slide. Now here the loss function has f in it. So if you care about the differentiability of f, I think h, then f has to be also differentiable, yes. Which means in its domain, ReLU is not, because it has a corner. And then we have to choose tan h or sigmoid because of that, or like
right. So having differentiability, it's actually pretty bad for the ReLU as well, right? Because this one place where it's not differentiable, so you want to deform it. Yes. So differentiability, I didn't add here. That is actually goes without saying, but this is exactly why this sinusoidal actually it doesn't perform well, because we never differentiate things, right? So we want things to move, change continuously, and if you have large enough jumps, then you will feel that the function is discontinuous. But you're absolutely right that having it being continuous and hopefully having its derivative be continuous, and all derivative be continuous, is essential. So those again goes into the discussions of pros and cons. If it is discontinuous, what should we do? If derivative is continuous, what should we do? Usually smooth it out, and then that will help.
Thank you.
Sure. Okay. Very well. So other questions? Perfect. Any other questions? No? Okay, good. Let me now stop the recording. Actually, I have to stop sharing, then I stop recording.